The universal sequential circuit model is important because we will be using this as a reference, okay, throughout our module 3, 4, and 5. So combinational logic, if you can take out all these, okay, let me just annotate. Yeah. So just assume that you are taking out all of these. You're not giving these inputs, okay. So this is going to function only as your combinational logic, okay. Now to this combinational logic, if in case I enable my memories, okay, if memories are enabled, that's when it actually gets converted to my sequential circuit model, okay. Fine. Now that we are clear with the differentiation between combinational and sequential, so we will continue our discussions. Fine. Now there is an important one more diagram here, okay, which is a general sequential circuit model with combinational logic functions separated into two blocks, okay. So you have two blocks here. One is the input, and this is combinational block 1 and combinational block 2, okay, and memory is in between. Now E is nothing but your excitation variables. These excitation variables are used to activate, okay, are used to activate your sequential circuit. Then the state variables are, after the memory, the output of memory is called state variable. See here, the output of memory. So this was your memory element. The output of memory was called your state variable. The inputs which gets into memory, okay, is nothing but your excitation variables. Keep in mind, inputs to memory is excitation. Output of memory is your state variables. Excitation, state variables. Okay. So if you can remember this diagram, okay, it will be easy for you to understand. So excitation variables are input to memory, state variables are output from a memory element. So I have a combinational logic here, which is one combinational logic 1, then another combinational circuit 2. Okay, so inputs are given as usual, okay, to both combinational circuit 1 and 2 together. Then my excitation variables are generated from the output of combinational circuit 1, and that is the input to memory. So whatever is my state variables, the output of memory will also get inside combinational logic. So which means what is happening here, memory and combinational logic are connected to each other. So memory and combinational logic input, okay, are connected. So the output of memory is connected to input of combinational logic here as well as here, okay. So combinational logic will have inputs as memory's output and the normal inputs. The normal inputs are these and the memory's output are these, okay. So parallelly it will receive inputs as well as memory outputs. So this is also receiving the same set of inputs, and here also we are having the same set of inputs. Now how do we activate these memories? These memories are activated based on clock. What is the purpose of clock, students? Can you tell me? Why is a clock used? Why do we need clock?
So for measuring the frequency.
Okay, that is fine. Generally, in general, why is clock used?
To time the input.
To
time the input.
Time the inputs, good. So what do we understand by timing the inputs? As soon as a clock is enabled, okay, so I am triggering the circuit to receive inputs, okay. As soon as there is another clock, I am triggering the circuit to receive another input. So this can be, said that it's a triggering circuit, okay. Clock can be referred to as triggering circuit. When I say we have class at this time, right, and you all um, come and meet together, it's all happening because of clock. If everyone has different clocks, then can we make up at the same time? I don't think so, right? So the only reason that we all are getting together is because of the clock. So clock should be synchronous, which means it should be the same. We shouldn't have different types of clocks. So the system will have a specific clock. So as soon as this clock is triggered, the outputs from your combinational circuits. Can you give me an example of combinational circuit, students? I want to know if you're aware of what is a combinational circuit. Mamta, can you answer that question?
Adder,
Sorry?
an adder, sir.
Okay, an adder and even your logical circuits, right? Your
Sir,
logical
encoder, decoder.
Yes, any logical circuit. It can be your AND gate, your inverters, your NAND, NOR, XOR, XNOR, okay, encoders, decoders, any logical circuit, anything that has an equation, anything that has a truth table, okay, so uh, is called a combinational logic. Just that, remember, it will not have a memory element, which means it is instantaneous. As soon as I give the inputs, it will work out inside and it will give me the outputs. So either you take the output or you store it somewhere, it is your headache. Okay. So the circuit will only compute based on the equation. So if I have AB plus BC plus CD, if that's an equation, I will design my circuit in such a way that it performs this function. So if this function is done, okay, the next task is, it generates outputs. If in case I'm adding a memory element to it, then I can call it as a what? I can call it as what?
Sequential.
Sequential, right? Correct. So I think we are clear with this diagram here, right? Okay. So for your benefit, for all of your benefit, I have written extra information, okay, uh, which is needed for your understanding. Whatever I have told so far, okay, is explained here. Okay, for example, binary input variables are from I0 to IN. It is presented, then the output variables, then we have state variables, then combinational logic has both system input and state variable inputs. Okay, so all that I have explained, I have put up here for your benefit. Right. So now we can actually look at some of the types of timing diagrams. Okay, some of the types of timing diagrams, and we can understand as to how these timing diagrams are. Okay, so before which we will just look into some of the theory behind this. Okay. So when we speak of memory in this context, we are referring to the ability to store binary data. Yes, we are aware of that. So how is memory implemented? With the help of what? Flip-flops, right? Flip-flop is the basic element of a memory, just like how cell is a basic element in your body, right? Cells are grouped together and then it forms a complex being. So similarly, flip-flops are the basic element of a memory. It is capable of storing about 1 bit. Okay. So I cascade, I combine flip-flops and then make it a huge memory. So, in previous days, for example, I can give you when they first were working out with memories, to transport a 4 MB memory, 4 MB, okay, 4 MB memory, they had to make use of an aeroplane, okay, to shift from one place to another place. Okay, so that huge was just 4 MB. Today, I don't think so. You will even get a song, of capacity within 4 MB, isn't it, students?
Yes, sir.
and your memory size is increasing in such a drastic manner that even your phones that you're using now has GBs of memory, right? 128 GB, 256, 512 phones have come with 512 MB, 512 GB, right? And you have this memory card slots which are capable of having um, capacities of TBs, right? 2 TBs. So what I'm trying to say here is there is a lot of innovation. There is a lot of things that are happening in the field of electronics, especially in the field of VLSI, very large scale integration. So which means a lot of transistors are combined and made complex circuits. Okay, right. So today 2 TB memory card can just be lifted with a single finger, right? But in those days, for 4 MB, they had to transport it using an aeroplane. So that's the technological advancements happening these days in your field. Right. The excitation inputs forces the memory elements, usually flip-flops, to desired state variable output values. So the output O is generated by combinational logic transform, which is G, and operating on input variables I and S. So what is this I and S? This is my I and this is my S. So this combinational circuit will work on I and S. I is input, S is your output of memory. Okay. So we can call that the output O is a function of I and S, right? So just a little bit of theory about it. So another key principle in sequential circuits is that memory data are free to change with time. Okay. So as the time changes, okay, the memory also does change based on the clock. So the clock input is not a binary value representing the time of day, but a synchronizing train of pulses. Now, this is important. Okay, it's a synchronizing train of pulses. So this you should note down actually. So what is a clock? A clock is a synchronizing train of pulses. Synchronizing memories changes its data only at certain amount of intervals. Right. So a distinction is made between the present state ST and the next state ST plus 1, when we can write your state. Okay, ST plus 1 is a function of input and present state. So ST plus 1. Okay, so where is this ST plus 1? So we will go back and we will try and understand as to where is this ST plus 1, right? So your output here that you are getting is going to be the next state. Okay, so that is ST is state plus 1, so next state. Okay, so this output is going to be your next state output. Okay, so this is actually working on the S and I. Yeah, so S and I, so state and input. So your next state is a function of, it's a combination of input and present state. ST is present state, ST plus 1 is next state, which means the next state is dependent on the present state, right? So if I want to know what is going to be the next state, then I will have to know what is the present state. So it's just like data analytics. Okay, if I want to know what is going to happen, after probably 5 years, if the same trend is on, then I will have to know what is the present trend, right? So it's only then I can predict the model and say what is it going to happen after 5 years. So your artificial intelligence, your machine learning works on this training model. Okay, so we train the systems so that it understands what is the present state, and then it understands, it analyzes, and gives us a model uh, prediction where it can tell us after a certain amount of time what is going to happen based on the present data. So here the present data that we are talking about is the present state. and st plus 1 that we are talking about is the next state, what is going to happen in the future. Okay. Input will change to st plus 1 on the next clock pulse. So before I press the clock pulse, what is going to be my next state? So I'm going to predict. So any doubts, students, till here? Till here, do you have any doubts? Please be interactive, okay? Do not just mute yourself and sit.
No, sir. No, sir.
Okay, fine. So now let's have a look at this clock signals and your Q1 and Q2. Fine. So my clock, as usual, as I told you, it's a synchronous train of pulses. Train is, it's a series of pulses. So it has its lows and high, and this is called my rise time. Okay, going from low to high, from high to low, it's called a fall time. So this is also called your clock edge. This is called your clock edge, and this is called your negative clock edge. Sometimes it's also called a falling clock edge. The reason why we use falling clock edge, because it's changing its value from a higher potential to a lower potential. So if the opposite happens, so it means it's a rising edge or positive clock edge, right? So these are some of the things that you should understand: rising edge, falling edge, negative edge, positive edge. Oh. So I will divide my time into even slots: t, t plus 1, t plus 2, 3, 4, okay, till t plus n. So these are my time durations, okay, and as my input passes, okay, q1 and q2 passes, so these are my signals. Next, we can actually see what is going to happen. Okay. The timing diagram is shown in the figure. A series of pulses called clock pulses, which produces the negative edge at times labeled t, t plus 1, t plus 2. So at every timestamp that I have represented, these are representing your falling clock, okay, or falling or negative edge of the clock. Sometimes in your problems, they might ask you to refer or use the positive edge of the clock. Okay, so in that case, you will have to refer to only these edges. Okay. So the reason why we have to know these falling edge, rising edge is because we have to know at what instant of time the data is going to change. Okay, is it changing for negative edge, or is it changing for positive edge of the clock? So whichever side of the pulse appears, it is that time that the data gets updated. Okay, say it had data from 0 to t. Okay, it had value 0. Okay, so let me just write it here. Okay, so from 0 to t, so for this timeline, what is the value of q2? Q2 is 0, is a low value. Q1 is also 0. Okay, so similarly I can check for the other timings. Okay, so here I can see for t to t plus 1 is also 0. Okay, this is also 0, also 0, and here it's going to change the value now in the next pulse, right? Here it is 0, and here what value is it? Here what value is it?
So
1, sir.
1, yeah, because it's a high pulse, so it's moving from a low value to a higher value. And similarly here you can see that it is 1, and this is also 1, right? 1, 0, 0, 0. Okay, so this is how I represent my values. okay, my binary values. So for instant from 0 to t, it is 0, 0. From t to t plus 1, it's also 0, 0. And from t plus 3 to t plus 4, it is 1, 0. T plus 4 to the next state, which is going to be t plus 5, is also 0, 0. So this is how we understand the waveform. This is how we see at what instant of time data is changing. Okay, so at this instant of time, the data is moving from a lower value to a higher value. Okay, so this is the point where it is actually transiting, okay, transiting to a higher value from a lower value, which is 0. Is that clear, students? Have you understood this waveform?
Yes, sir.
Okay, fine. So similarly, okay, we will move on and see these kind of waveforms a lot in this module. Okay, so if you have understood whatever I've explained so far, then that should be absolutely fine for you to understand the upcoming concepts. Okay. So variables Q1 and Q2 are free to change value only on the falling edge of the clock signals. Okay. So only at the falling edge we're going to see them. Q1 and Q2 are the state variables that change as shown in figure. Because two variables can have four permutations, which is 0, 0, 0, 1, 1, 0, 1, 1. Each state becomes a present state after a clock. So once there is a clock given, then it becomes a present state. Before a clock and you're predicting what is going to happen next, you're going to predict your output as to what I'm going to receive. So that is going to be your next state. Okay. And we'll go to a next state on the next clock pulse. When we write ST, we mean that the state at some clock time t. So this t can be t plus 1, or it can be t plus 3, or it can be t plus 4, but some t. Okay. The next state t plus 1, okay, st plus 1 will occur on the next clock pulse. So I think now you have understood the concept of present state, next state, state variables, excitation variables, combinational logic, sequential logic, memory elements, right? So I hope all these concepts are clear with all of you. Any doubts? You want me to repeat any section now?
Sir, the excitation and state variables, can you just explain it once again?
Fine. So let's get back here. So excitation variables, we get it from the combinational logic. Okay, so whatever output that we get from combinational logic, those are called as excitation variables. Those are which are the output of memory element, okay, which comes out from the memory element is nothing but your state variable. So state is relating to memory, excitation is relating to your combinational circuits output values. Okay. So we will be doing a lot of exercise based on these state variables and excitation variables in the upcoming classes, where I will just show you a glimpse of it as to how we will solve problems based on these tables. Okay. Now, yeah, let me go to the problem section. So here we will be developing something called excitation table. Okay, and here we will be developing something called characteristic table. Okay, so using these two kinds of tables, what we will do is we will try and design, or we will try and solve problems. Okay, so I need the truth table, I need the excitation table, I need to know how the flip-flop is, then I need to know what my output is going to be. Okay, and for flip-flop conversion from one flip-flop, if I have D input, then I want to actually use JK flip-flop, then how do I convert? Okay, so this is nothing but your Qn plus 1. Qn is your output and your Qn is the next state. Okay, so this is your characteristic equation. So we will learn all of these. We have a lot of exercises to do, okay, with respect to excitation table, with respect to your state variables. Okay, so I've just given you a glimpse of it as to how we are going to look into it. So as of now, you remember your excitation is going to be the output from your combinational logic, okay, and your state table is going to be uh, given to input of your combinational logic, and that is actually the source is the output of memory element. Okay, memory element M. Fine, Sayan, can I continue?
Yes, sir.
Okay, so yeah, we saw this. The next topic that we have is basic bistable element. What is bi? Bi means
Two.
what? Two, right? Just like how we have binary, binary means 0 and 1, right? So bistables, so stable states are two. So I call it as bistable element. So this is a basic element that you see here, okay, which is making use of an inverter. Okay, so if you see here, x is going to give x bar, and once I give this here to my other input, okay, to my other input, that is actually going to be inverted, and I'm going to get q bar. Okay, so q is my normal input, q bar is my complemented input. So x bar, y bar. So this is my q. Q means just the output of the stage, the upper stage, and q bar is going to be the complemented version of q. So if q is 0, then q bar is going to be 1. So what do we understand by this? We're going to have two states. The first state is the high state and the other one is the low state. Suppose I give x bar here, then I'm going to get x as my output. Right? The normal way of representing our inverter. Any doubts here, students? Basic bistable element. Okay, so we will just go through the information so that it becomes easy for us to take off from the other topics. Central to all flip-flop circuits is the basic bistable element. So this is going to be our basic element that we will be using for our explanation concepts. So this circuit has two outputs, which is Q and Q bar, which I've already mentioned. As seen from the figure, it consists of two cross-coupled NOT gates. So what do you mean by cross-coupled? The output of one is actually connected to the output of input of the other. So which means till I get the output of the first inverter, I will actually not be able to check what is my output of the second stage, right? Because it is dependent here, it is dependent on this output. So as soon as the output comes here, immediately it will come and it will enter as my input here. So that is going to be used as my processing for my input, okay, and it's going to come out as the complemented version of this. Okay, so which means if I have x bar here, okay, technically speaking, I should be getting x here, right? I should be getting x. So this x is actually connected here, isn't it? And this y is connected here. Okay, fine. Q bar, second gate serving as input. Clearly, this structure involves feedback, right? So this is nothing but called feedback. Part of the output when it's given to input, it's called a feedback. Okay, so now we will do some workout here. Okay. First, assume x is equal to 0 in the figure. The output of the upper NOT gate is then 1. That is q is equal to x bar is equal to 1. Since the output of the upper NOT gate is the input to the lower NOT gate, x bar is equal to y is equal to 1. Understood, students? I gave 0 here, so which means I'm getting 1. So x bar is equal to 1, and 1 comes here, so which means x bar is equal to y is equal to 1. So 1 comes out here, and this is going to be my 0. So 0 is again going back here. So 0 is here, 1 as my output. Consequently, the output of lower NOT gate, that is y bar, is equal to 0. Okay. Why is it 0? Because I got 1 here and 1 comes. There's an inverter, so I should be getting the 0. However, since the output of the lower NOT gate is connected to the input of the upper NOT gate, Q bar is equal to y bar is equal to x is equal to 0. So many things are connected. Q bar is equal to y bar is equal to x is equal to the initial state that we gave was 0. Any doubts here, students?
No, sir.
No, sir.
Okay. So we are just, instead of using x and y, we are trying to put the binary value 0 and 1. That's it. Simple. Okay. However, since the output of lower NOT gate is connected to the input, so 0 is there. This is precisely what we assume to be the value of x, right? So we had assumed initially what? X is equal to 0. So that is also working out, because here also we are getting 0. Because we got 1, 1 is coming here, 0, we had assumed x is equal to 0. So which means this is actually working out for us. Thus, the circuit is stable with Q bar is equal to 0 and Q is equal to 1. Similarly, it is easy to show that if it is assumed that x is equal to 1, the reverse, right? The reverse happens as a result of having two stable conditions. So what are these two stable conditions? 0 and 1. Okay, so it is called your bistable basic element. Okay, basic bistable element. So this is used to store values, okay, or state of the element. It is given by the signal value at Q output terminal. So whatever output I'm getting here, okay, this value is very much important. The value of Q is important because it is my normal output and it is going as input to the next stage, right? So it's very important. Most of the times, if you know the value of Q, you don't have to calculate the value of Q bar, because you know that it's a complemented version of Q, right? So you really don't have to check for the value of Q. Q bar, if you know the value of Q. Okay, fine. When the device is storing 1, it is said to be in one state or set. Keep this in mind. When it is storing 1, then we call it as set. On the other hand, when the device is storing a 0, it is called reset. 0 reset, 1 set. Okay. There can be a metastable state. So what is a metastable state? Something in between logic 0 and 1. Okay. So can someone tell me, did we already see a metastable state here in our discussion? Is there any metastable state here?
Sir, the varying line.
The varying line, right? So which means if I say what is the value at this point, okay, so yeah, so if I say what is the value at this point, then it is a metastable state, isn't it? It is not 0, nor has it reached the high value 1. It is in between, right? So this can be termed as your metastable state. Okay, so I hope you are able to follow the concept of metastable. So this is about your basic element, basic bistable element. So latches we will continue in the next session. We'll continue our discussion with latches. Up till now you have seen about the basic bistable element, okay, which is capable of having the values. Whenever 0 is given, 1 comes here, 0, so the same value is retained, right? So which means this is working as a simple memory element, right? So now we will look into something called latches. Latches is also a storage device, one class of flip-flops. It's a class of flip-flops. This class is characterized by the fact that the timing of the output changes are not controlled. So that's the only thing here. The output changes is not in control. Okay, that is, the output essentially responds immediately to changes on the input lines. So whenever there is a change in the input line, okay, so your output will immediately start there will be a variation in the outputs. Okay, so that is one downside of latches. Output essentially responds immediately to changes on the input lines, although a special control signal called enable or clock might also need to be present. So if I enable, then only it's going to work. If I disable, then it's not going to work. Thus, the input lines are continuously being interrogated, so which means it is always sensing what is at my input side and it is checking, right? So the first one that we are going to see here is your SR latch. Okay, the SR latch. So SR is also called as set reset. So which means set is used for when the value is 1 and reset is used when the value is 0, right? Okay. So for creating an SR latch, okay, we will be making use of a NOR gate. Okay. So OR along with NOT, OR along with NOT. Okay. So in simple, you can actually refer to the first diagram here, and these both of these diagrams are the same. Figure shows the SR latch that consists of two cross-coupled NOR gates. When I say cross-coupled, always make sure that you understand that part of the output is the input to the next stage. Okay. It has two inputs and two outputs. When S and R both are 0, the logic diagram simplifies to the basic bistable element, that is cross-coupling of two NOT gates. Thus, the latch is in one of the two stable states when inputs are applied. Okay, so we will see here. Whenever I have my inputs 0, 0, 0, 1, 1, 0, 1, 1, this is going to be my combination. Okay, and my outputs are going to be Q and Q bar. So here I have used Q plus and Q plus bar. So instead, you can even write it as output and output bar, or Q and Q bar. Okay. So, and this is your basic representation of your SR flip-flop. SR are your inputs, Q and Q bar are your outputs. Okay. Sometimes few authors also represent it in this fashion. They don't write a Q bar here. Instead, both they write Q and Q, and they use a small bubble here, okay, representing that it's a low value of Q. So get used to both of the conventions. The most used general type convention is this, okay, where I have S, R, Q, and Q bar. Right. Okay. Now let's understand as to how this circuit works. Now let us take the value S is equal to 0 and R is also 0. Okay. So when I have these values, which is 0 and 0, Okay, 0 and 0. Now I have to find out as to what is going to happen. So anything that gets added with 0, okay, so I am not sure as to what my output is going to be, right? Because I don't know what is my input here. So unless I have one of the input, okay, let us assume, that the value here was 1, okay. So 0 plus 1 is going to be 1, and that is going to be inverted, and I'm going to have what is my output now? What is my output here? 0 nor 1. What is my output?
0.
0, right? So 0 is going to come and sit here. So once I have my 0 here, now I know what is the value here of my other input, right? So this value is also going to be 0, right? So 0 and 0. Now again, what is the value going to be? 0 plus 0 is 0, and I have to note it. So which means I'm going to get a 1. Okay, so whatever we have assumed, so that is actually correct. Okay, we had assumed 1, so 1 is also coming here. So ultimately my value of q, okay, is going to be 0, and q bar is going to be 1. Now here the reason why I have written q and q bar is because whatever was there previously, okay, now say I have offed it, okay, and I have kept it. So previous values, now I switch it on, and then I want to know what values are there. Okay, so forget about owning and offing. Just if my values are 0, okay, whatever values were there previously. So previously we had computed that the values were 0 and 1. The same thing will be there. So which means q is equal to 0 and q bar is equal to 1. Now let's go to the next case. Okay, next case when your S is 0 and when your R is 1. Okay, so S is 0 and R is 1. Now that I have a sure uh, information that even if I get 1 here, what is going to be my output? What is going to be my output here? My input is 1 here. Okay, so irrespective of whatever comes here, what is my output?
0.
Okay, because 1 plus 1 is 1 and not I get a 0. Good. Even if I have a 0 here, 1 plus 0, I will get a 1 inverted 0. Okay, so this 0 is going and coming and sitting here. Okay, so once I have 0, 0, I'm going to get 1. This 1 will come and sit here. Okay, so which means whatever we had assumed, okay, it is working out. So are we getting 0 and 1 here? Understood? Understood how we got 0 and 1, students? So 0 and 1. Is that clear, students, as to how we got your 0 and 1? Yeah. So similarly, what you have to do is you will have to put these inputs accordingly towards your gate and try and understand what is your outputs. Okay. So by this we understand, okay, we summarize, and then we say that your SR flip-flop, whenever it has 1, 0, the Q is going to be 1 and Q bar is going to be 0. When it is 0, 1, it's going to be 0, 1. Okay, fine. And when it is high, it's actually going to be unpredictable, which means it's going to be in a toggle state. Okay, so I think we will probably stop here, okay, with our discussion of SR latch. Okay, and then we will continue, okay, in the next class, seeing as to how we can use this as an application. Okay, the application is going to be a switch debouncer, most repeated question in your examinations. Okay, so we will look into that application. So before that, we will just read a few information that we have already seen, okay, just to make sure that everything is in controlled. So 1 on the R input, 0 on the S input results in the latch being reset. Okay, so 1 and 0. Okay, so I'm getting 1, 0. If the input R is subsequently returned to 0, then the latch retains its present state. So 0, 0, which means the present state Q and Q bar. Okay. As described by first row of the function table. Since Q bar is equal to 1, maintains outputs 0 and 1. So whatever was there previously, okay, so the same thing will be there. Similarly, for S is 1 and R is 0, you're going to get this combination. The event when both inputs, when both are high, S is equal to 1 and R is equal to 1, okay, it returns a 0 simultaneously. The device may enter into metastable. So metastable is something called a toggle state, 0, 1, 0, 1. It keeps toggling. Okay, so that's why I've given a 0 and with a star called unpredictable behavior. Okay, and this unpredictable behavior we do not need. Okay, we do not want this kind of toggling states. Eventually the device becomes stable, but its final state is unpredictable. So I do not know if it's going to be a 0 or it's going to be a 1. So it's totally unpredictable. Okay, so this will actually cause noise. Okay, it will cause disturbances or unwanted signals because of this toggling effect. Since the changes on S and R inputs are immediately affect the outputs of the latch, S and R inputs are regarded as asynchronous because your outputs are fully dependent on the combination of input values. As soon as you change the values here, immediately the outputs also does change. So this kind of behavior is called asynchronous type of behavior. Okay, so we will stop here and we will continue in the next class.